Here we're trying to compare analysis of a three-span continuous bridge. We're trying to use we're trying to make a comparison between a 3D finite element analysis versus just a regular 2D. For the softwares we used STAAD Pro as just a 2D analysis, and we're using Larsa 4D as a 3D analysis. So the bridge geometry is basically a three-span continuous, 100 foot in each span. What we're trying to achieve here is trying to get the maximum positive bending moment, and make a comparison of what the positive bending moment is in 3D as compared to 2D analysis, and calculating the distribution factor and getting the final moment for the positive bending moment. So we start with the section property. As you could see here, we have a 60 inches total depth steel plate girder. We have a 1 inch thickness for the flange, 0.56 inches thickness for the web, and 1 inch thickness for the bottom flange. Both top and bottom flanges have 16 inches width. We came up here with a 64.48 area, total area for the whole plate, and it did all the calculation to get the inertia at the neutral axis, and it came out to be 36,955.89 inches to the fourth. As a comparison, if we get the right calculations of the properties, it checks out 36,955 for inertia. We need this calculation to come up with the distribution factor. So based on the distribution factor calculation, after we calculate all the section properties, we have all the distribution factor for a 2 or 3 lanes loaded, 0.863. The geometry of the bridge, we have the spacing of the girder to girder spacing at 12 feet. These are all needed to calculate the distribution factor of 0.863. The distribution factor is found in the AASHTO. I don't have to go intense to that, but yeah. So for 2D, we did we put up the geometry of the three-span bridge. It's basically a 100 foot span. We have the fix here at the center. Oh no, at the first interior pier. Then we ran a truckload moving load analysis, starting from at the beginning. It's it says an HS20 truck, and then we have it forward every 5 feet, and we came up with the maximum moment for the positive bending moment at a maximum bending moment. That's for the lane load, 646 kip feet. Normally STAAD Pro have their moment down for the positive moment down, and then their negative moments is up. It's kind of like the opposite of what I'm kind of used to. That's for the lane load. Now we select the case for just the let's do a moving load. Okay. So we came up with the maximum possible moment as 1,210 kip feet for the truckload. I believe that's, if I'm not mistaken, that's probably the load generation 10. Yeah, about here. So that's the maximum maximum positive moment for the truck. 1,210 kip feet. We have to multiply this by 33% for the dynamic load allowance. We add this to the lane load, which is this. Oops. This lane load right here. We get 646. We came up here. We get 647 and 1210. For the lane load, we came up to be 559 for the first interior girder. That's the distribution factor. We multiplied that to that. We multiplied this to the distribution factor. We multiplied by 33%. We have the total maximum positive moment of 1,947 feet. Now this still have to be multiplied by 1.75 factored load for live load. So multiply by 1.75, but for now we'll just leave it this way for our next calculation. Now, so we got the maximum moment at 1,947 feet for a 2D analysis. That is given calculating the distribution factor and all. Now we make a comparison to 3D load analysis, 3D live load analysis for moving. So as you could see, we have a the end game for like using a 3D analysis is to no longer use distribution factors as a way of calculating the maximum bending moment. Instead, we put in the maximum number of trucks along the bridge and finding out the maximum bending moment. Of course, that would also but then we have to use the what you call multi-presence factor included to the calculations. So if you have, like, for example, 3 lanes loaded in a bridge, you'll need to put in the multi-presence factor of 1.2. If it's only like 1 lane loaded, 2 lanes loaded, it will have a multi-presence factor of 1. 3 lanes loaded, the multi-presence factor is 0.85, and 4 it will be 0.65. We have the design lane width of 12 feet, and you'll have your vehicular loadings. It's like an HS20 truck. Here you have the front and back spacing. This is mostly for like a negative to get the maximum negative moment at the support. So for now we'll just have our concern is just to get the maximum positive moment at the center of the span. So as you could see here, you could see all these the lanes loaded right here. We have 1 lane, 2 lanes, the 3rd lane. The small ones right here are the lane load, and then these are the 3 truck loads. As you can see, when I use this selection point right here, they push this pointer tool to find in the maximum bending moment at the center. So it tells me that the maximum moment is here. The truck would have to be here to generate the maximum positive moment. And then the lane load would have to be loaded here in this span and loaded in that span. Similar to what we did on in our STAAD Pro. We have the lane load loaded in this span and loaded in that span. You'll have the maximum moment at 646 kip feet for the lane load. If you go here, it also tells you that the lane load is, in order to get the maximum positive moment for the lane load, you have to load it here and load it here. But this one was done by the software automatically. Once you put in, it'll figure out for you where the maximum positive moment is. Because what it did was, first it did influence surface analysis and finding the maximum influence coefficients. It puts the truck to that location. So now, comparing where the maximum bending moments is for the positive moment, we go right here for this command. Normally we say, now we have to find the global bending moment. So if you could see, it's Z, Y, X. So the bending moment, global bending moment, will be about the Y axis. So it should be moment Y. Normally, if you we have a 100-foot span. Normally the bending moment, the maximum positive bending moment, is located at 0.4 L, and in this case it's 40 foot from the beginning of the span. Before I did this earlier, I did some groupings. I grouped the deck plates and the first interior girder together. So this is our point of this is our point of this is the one that we're trying to get what the maximum bending moment is. So if I hide the selection, you complete rendering. So we have a same thing. We have a 60-foot steel plate girder here. Same properties as the one we calculated a while ago. So we group this together in order for it to generate the maximum positive for the compound for a compound section, meaning there are they're composite together. So getting the maximum moment, positive bending moment at a particular position, you get 40 feet from the beginning of the bridge, and then came out 1,840. This is with including the impact load, 33% additional impact load for the trucks, and adding the lane load. So comparing our answers to the 2D analysis, wherein we calculated our distribution factor. Our 2D analysis is a lot more conservative. It's we have 1,947 or 1,948 kip feet as compared to our 3D analysis. Now, of course, we still have to multiply this by 1.75 to get for the factor for live load. Yeah, there you go. There you have it. We have turns out the now I haven't run any other sections, whether it's this is most if 2D analysis is more conservative or not. This is just one section that I ran, but just for this element section came out that our 2D analysis is more conservative than a 3D analysis. I have not really shown you how I develop all the geometry for the, but that's for this video is just for a comparison between a 3D and a 2D analysis. There you have it. Let me just show all the show all the 3D rendering for the bridge. It's a 100-foot span in each 100-foot span in each span. We have 3 spans. That's a 3D analysis of you, and this is our 3D analysis. This is also, we could also see this in 3D. Now we could also do a 3D model in StatPro, but I think Larsa is more. Larsa 4D is a lot more, a lot better when it does the 3D analysis for moving load at least. Okay, that ends our video.